What's up, everyone? How are you all? Sean with Create Your Lifestyle Academy. And in this episode, we are going to talk about measurement, calculations, and error as they relate to the scientific method. So in the episode 1, I explained what the scientific method is. It's a process, the most fundamental process in all of science, irrelevant of the subgenre. And in this episode, we're going to dive in a little bit more, focusing on the experiment/analysis portion as it relates to measurements, the calculations we make, and the error associated with those calculations. Because that overall is going to determine how useful our experimental process was in finding information that can be applied for societal benefit. So I'm going to write this down on the board: measurements, calculations, and error. Alright, so the measurement, as we'll define it, is a value assigned to the object of interest that allows us to extrapolate information. And so, before I kind of dive into any more detail, I want to iron out some things and explain just how we use the measurements. Okay. So first off, measurements come in two forms: qualitative, meaning it's non-numerical and it's more so subjective, and then there's quantitative, meaning that there's a numerical value assigned and it is more so objective. So I'm going to write that down too so you all can see. So I'm going to let you all look at that for about 2-3 seconds just to make sure you got everything in your notes if you're taking notes, or if you're watching this for leisure, just to sum up everything I've said so far. And so just to give you an example of a qualitative measurement, we can say Sean is average height for a American male. And if you want to make that a quantitative measurement, you say, straight up, you just say Sean is 5'10". And so just to show you how those what's the word I'm looking for? I'm thinking the word I'm looking for is revolve around each other. You can say, qualitatively speaking, you say Sean is average height. So that can be a range of things, right? You can say average height is between 5'8" and 5'11" for an American male. So if you were to say, if someone was describing me to another human being, they say, okay, cool, average height for American male. You start to formulate a picture, and then you then assign a quantitative measurement to height, and now you can say, oh, okay, I'm starting to get things become more concrete, more objective. It's straight to the point, instead of having that wiggly room or being stuck in limbo for the qualitative. But still, both are useful. Another example real quick, you can say, the writing on the wall is dark red. That's a qualitative. Quantitative would be, the red on the board is equivalent to a specific amount of diluted color standard, right? And I'm not going to say what it is. I don't know what it is. I'm just saying that's an example. Moving on. In the context of an experiment, measurements, whether qualitative or quantitative, can be what we call accurate or precise, okay? And sometimes they're both. And so I'm going to erase all this. So you have accuracy on top and the precision on the bottom. And so measurements can be accurate or precise, or they can be both. And ideally you want them to be both when conducting an experiment. Just to bring you back into why we're even talking about this in the first place, is because that when we conduct experiments, the whole point of experiments is to find out useful information that can allow for societal benefit. Don't forget that. And so for accuracy, the measurement is considered accurate if it's close to a known exact value. Precise measurement that is close to other measurements made by the operator in the experiment. And so, let's say actually before I give you a scenario, I want to say measurement that is close to other measurements made in the experiment or the series of the ecosystem in which we're playing, okay? Actually, we'll just say experiment. We'll say experiment, because cool. So going back to the height example, okay? You say measurement that is close to a known exact value. If you were to say Sean is 5'11", that would be accurate. Because it's close to the known exact value. I'm actually 5'10" and 3/4 inches tall. So 5 feet, 10, 3/4 inches tall. Cool. But if you were to say just Sean is 5'11", that's still accurate because it's off by 0.25 inches. Precise would, an example of precision of measurements would be to say that if I was to go to like 4 doctors because I had a serious health condition and they were going to give me a physical, and you were to say, for doctor height in feet and inches. One doctor says I'm 5'10". One doctor says let's write it down. So doctor number 1 said I'm 5'10", doctor number 2 said I'm 5'11", doctor number 3 said I'm 5'10", 5'10" and a half inches tall. Doctor number 4 said I'm 5'11". That's pretty precise. The outlier in this case, in my opinion, would be number 1 because I'm actually 5 feet 10 and 3/4 inches tall. And so the last 3 measurements are they're more accurate. So that's the outlier right here. But all these are still precise, is what I'm saying. They're all close to the measurements and the assessment / experiment are close to each other. And that's why they would be considered precise in this case. So, for this experiment, you say the known value is 5'10" and 3/4. One doctor said I'm 5'11". Cool, that's accurate. Precise for this scenario, the 4 doctors gave EJ values that were all close to each other. So there's some similarities going on here, right? There's a pattern that can be detected. There's a universality that's occurring here. We can use this because it's precise. So yeah, it works out. And I want to say one more thing. Sometimes the measurements can be precise but not accurate, and this is where we get into trouble. So ideally, we want measurements to be accurate and precise. So if we were to change all these numbers up and say doctors 5, 6, 7, and 8, another 4 doctors would say Sean 5'6", 5'7", 5'3", 5'2". First of all, those measurements aren't precise at all, and I'd sue because the doctor would not be those doctors wouldn't be reliable. Second of all, that's just not true because if you were to see me in person, he's 5'11". And so I can talk about this all day, but you get the gist, and I'll give you some examples in another video where you can like automate this information in your brain. And so now we're going to talk about calculations. Okay. So calculations are important because we're messing with numbers and we want to make the numbers as useful as possible for us, and it's all for societal benefit. It's really important you explain that we are trying to benefit society as a whole. We're not being selfish with this stuff. So I'm going to take the tabulated data and convert it straight inches. And so, this is my height in inches, okay? And so, calculations, basically, to make a long story short, we as scientists use SI units, or International System of Units. SI units is a fancy way of saying International System of Units, and it actually means, it's actually pronounced like System International, something. It's French. I can't pronounce it because I don't speak French. But basically, International System of Units, which is the metric system. The benefit of the metric system is that everything goes by a factor of 10. So when you want to convert things and make calculations, and you're making conversions, they go by factors of 10 if you want to make them bigger or smaller. For example, 1,000 meters is 1 kilometer. All you do is move the decimal point, which is very convenient for scientific purposes. Another insert in here I want to make is that basically, if you're off by a factor of 10 or 100, you did the calculation right, but you just misplaced the decimal point. But if you're off by a factor of like 3.28, that means that you just were all together incorrect in your process. But we'll get to that in a minute. So my height in inches is 70, according to inches, it's called Dr. 1. 71, 70.5, 71. And so now we get into calculations. In science, the number gives us more information than in colloquial terms. Hey, Diamond, get down, get down, get down. And so, basically, a measurement based on the number alone gives us information on how accurate or precise basically the measurement gives us information on how useful we can and how reliable it is. And this is where the term significant figures comes in. So I'm going to write that down. I'm going to write that over here. And man, this can really trip a lot of people up, so I want you to pay attention, okay? The correct term is significant figures, but I also want to say that another way to verbalize this concept is to say important figures, or reliability of figures, or trustworthy figures. So the word significant trips a lot of people up. So it's like, oh my gosh, like they just start making all these things up. But a significant figure is basically the figures that are important, or the figures that are significant in a measurement or a calculation. And that gives us information on how accurate or precise we actually are when we make the measurement. So, for example, height is 70 inches, right? But there's no decimal point after. So, in fundamental mathematics classes, you're taught to round up. So, in actuality, when the doctor was measuring me, that could have been 69.8, and he just rounded up to 70. And there's no decimal point. But if there was a decimal point, we could say, okay, that is definitely 70.0 on the dot. You know what I'm saying? And so in relation to that, you see 70.5. It's not 70.50. And so if the measurement was 70.46, he could have very well just rounded up to 70.5 for convention or convenience sake. And that's the result we see in the report. So it's very important to get these significant figures out. I'm gonna write down the rules later, but I just wanted to give you a brief introduction of that. We're gonna go to calculations. And the significant figures relate to calculations, so that's why I wanted to give that brief stint. And so we're about to do a conversion calculation. And that's why I mentioned significant figures. You ready? All right. So we're going to convert all these inches, which is not scientific units, to SI units. And so the conversion factor I used to convert inches to centimeters, I multiply by 2.53 because there are 2.53 centimeters in 1 inch. And so this is what I got when you do the exact calculations. It's very simple. But this is where the significant figures come in. And the significant figures and to give us an indication of how erroneous we are. So, these tabulated values aren't factored in with the significant figure rules. My cat. All right. I'm gonna erase the first three columns because they're not important anymore. So now so basically I did this conversion calculation to segue into errors. We're about to wrap up. Give me another 5 minutes. So basically there are three kinds of errors. There's systematic errors, random errors, and then there's human error. Now, which one do you think the operator has more control over? Human error, right? Actually, the operator has control over all three, but not as directly as the human error. So, I'm gonna write this down. Alright, so basically the systematic error comes from errors from the process. Long story short, you don't want to have a process that is extremely long. So for example, if a process has 7 steps, there's more error associated with that process than from a process that has 4 steps. Now, random error comes from you don't know what. For example, it could be due to the temperature of the lab, the surface that you're doing things with, the equipment that you're using, and that error comes into play when you're making measurements. And there's human error. For example, you could say Trey does something like he just has a tendency. You can say like Trey has an over tendency to measure things and round up too much, right? So he doesn't. So he like gives a overly high result even though he doesn't mean to. And so the errors really helps put the experiment and the data analysis into context so that other people can assess the validity of your process. So how does this relate to the doctor measurements? That's what you're asking. I'm gonna wrap it up in like 2 minutes. Basically, the number associated with the measurements, not all these numbers are important. And that's why I mentioned significant figures earlier. Not all these numbers are important. And so basically there are rules when you multiply or divide I'm gonna write it down here. A little squiggly line to divide. Divide numbers. All right, so basically significant figures rules really quick. When you multiply and divide, number of numbers used, those are significant. Basically what I mean, so example, I multiplied 70 times 2.53. There's a total of 5 significant figures. And so, I'm about to say number of significant figures used, sorry. Yeah, number of significant figures total. And when you add or subtract, it's by the decimal point. So if we were to add all these heights together, we would basically ignore this 5 and not even factor it into a calculation because we can't be sure that that 5 is trustworthy, is significant. That's what we mean. We can't trust that. So we have to omit it for the sake of our processability. And so, in summation, we talked about measurements, calculation, and errors, and the subtopics of those of measurements are qualitative and quantitative. Those are the two forms measurement come in, and measurements can be accurate or precise, and we wanted them to be both ideally. It makes our process more valid. It gives our process more integrity. We can be more trusted as scientists. Calculations. In relation to calculations, don't forget we use the SI units, International System of Units. Basically, liters for volume, grams for mass, seconds for time, joules for energy, Kelvin for temperature, so on and so forth. And then don't forget about significant figures. Now, significant figures are indicator of how trustworthy the number that was measured or the calculation that was calculated is. And so don't forget, when we multiply, we include all the significant figures used in that calculation. And when we add or subtract, that's the number of numbers after the decimal point. The number of significant figures after the decimal point, that's the number of significant figures we keep, the lowest number. And then errors. Don't forget, errors can be human, that's the nature of that operator, the error associated with the nature of the operator. Random, basically the various idiosyncrasies associated with the process you design, the errors associated with that, that's a random error. And then there's systematic error. Errors associated with things such as the machine or the type of equipment you're using. So that's about it. Hope you enjoyed this episode. If you have any questions or want me to make another video, I'm going to make another video on significant figures just to clarify that up, because it is a really hard subject and maybe practice problems. But hope you all enjoyed this video. Once again, Sean Patterson, Create Your Lifestyle Academy, Beyond the Bonds, episode dos. Thank you for your time and have a good day. Bye.